Hello, welcome to episode 2 of Maths in an Empty Classroom with me, Mr. Southern. We're going to talk now about connected particles on inclined planes. You should have watched the first episode to lead into this. There was a little bit of theory in that, so if you haven't watched the first episode, please watch the first episode before cracking into this. What I would suggest that you do though is have a look at this example, and using what we talked about in episode 1, try and have a go at it yourself. Try and draw the diagram, label all the forces, think about what's happening to the system. Okay, so pause the video, have a go, and then when you've had a go, restart the video and see if what you've got matches what I'm about to say. Here we go. So we have particle A of mass 4 kilograms rests on a rough inclined plane making an angle 30 degrees to the horizontal. The coefficient of friction between A and the plane is 0.15. A is connected to particle B of mass 7 kilograms by a light inextensible string which lies along a line of greatest slope of the plane and passes over a smooth fixed pulley at the top of the plane. B is hanging freely above a horizontal plane. Oh my goodness me. Right. Let's start with the diagram. It is impossible to answer mechanics questions without drawing a diagram, and that is not a challenge, that is a statement. Okay. So, let's start off by drawing a nice big diagram. So, we have an inclined plane. Nice big inclined plane, and we were told that the plane was inclined at 30 degrees to the horizontal, which is going to be that angle there. What I now need is a mass A, which I'm just going to draw there, drag over and spin it around so it lines up nicely like so. And that is particle A, and we were told that particle A has a mass of 4 kilograms. So let's add that onto our diagram, that we have A here, and that has a mass of 4 kilograms. Okay. We were told that it's connected by a light inextensible string passing over a smooth fixed pulley, and then we have another particle, particle B, which hangs freely, and we were told that particle B had a mass of 7 kilograms. So we've dealt with the fact that particle B of mass 7 kilograms by a light inextensible string. We already dealt with the angle being 30 degrees. And I'm just going to make a note at this point that the coefficient of friction between A and the plane is 0.15. I'm just going to go to the next page there and just make a note over here that mu, the coefficient of friction, is 0.15. Now, importantly, if you watch the previous video, you'll remember that I said that it's important to know which direction the system's moving, because that's going to have an effect on how we draw on the frictional force. So it says here, when the system is released from rest with the string taut, A moves up the plane. So to acknowledge that, what I'm going to do is I'm going to do an arrow like that with 2 dashes on it, and I'm going to label that A. If particle A is moving up the plane, then clearly particle B must be moving down, so I will label that same acceleration as well. So these two particles are going to move with the same acceleration, and we can assume that because we were told in the example that the string is light and inextensible. So light and inextensible string means that those two particles are going to accelerate at the same rate as each other. That's one of the modelling assumptions that we're often asked about at the end of these questions. Okay. Right, so we're going to be finding the initial acceleration of A and the tension in the string. To be able to do that, I need to consider all the forces that are acting on each of the particles in the system. So let's begin by labelling the weight of A. Now the weight of A acts directly vertically downwards, and it's 4g mass times gravity, 4 times g. And remember that g in maths is 9.8. We'll come to that later on. Now, remember what I said in the first video, which is whenever you've got a force in this situation that's not acting parallel or perpendicular to the plane, you draw in a little dashed line, and the angle you create between the dashed line and the force will be the same angle as you've got there. So in this case, 30 degrees. And what I'm going to do while I'm there is I'm going to label on here by joining up my right angled triangle. I always forget to take the dashed line off. That this force here acting perpendicular to the slope is going to be 4g cos 30, and that this force here acting parallel to the slope is 4g sine 30. Now that is the parallel component of A's weight, and if you remember from the first video I said that is the one that people always forget to think about. So avoid that by labelling it first. Other forces acting on A. We have the normal reaction force, which acts perpendicular to the plane. We have a tension in the string here, and another tension in the string here. Now remember, this one acts on the particle A, this one acts on the pulley. Now, which way is it moving? Well, I don't have to go back and reread the question, because the fact that I labelled that the acceleration is going to go this way means that A is moving up the plane, and that is very, very important, because what that means is that my frictional force is going to act down the slope, because friction will oppose the direction of motion. So if A is moving up, friction is acting down. Label friction with a small f, please. Right, that is all the forces considered acting on A. So let's just now get the forces acting on B. Again, we have its weight acting vertically downwards, which in this case is 7g, mass times gravity. We have a tension force acting on B upwards, and we have another tension force acting downwards on the pulley. And as we know, all four of these T's, these tensions, they're all the same magnitude, same value, same number. Now we've labelled all the forces on the diagram, what we need to consider is what forces are acting on each particle causing its motion. We're going to set up some equations, and that's going to allow us to find the acceleration and to find the tension. So, let's begin with part A. The first thing that we always do is that we resolve perpendicular to the plane. And when I talk about perpendicular to the plane, I'm talking about any forces that, if I move a ruler across here, are acting along the ruler. So as I hit this point here, I can see that I've got two forces. I've got R, and I've got the perpendicular component of weight, which is 4g cos 30, and there are no others. Now those two forces must be equal and balanced, and I know that because A is sliding along the plane. It's not being lifted off the plane or pushed into the plane, it's just sliding along it. So therefore, the normal reaction force must equal 4g cos 30. Now, the purpose of finding that is to work out a value for friction. So having resolved perpendicular, I should say, to the plane, we're going to find a value for friction. And to do that, we're going to use the fact that friction, or the maximum friction, is mu times by the normal reaction force. Now I know from the question that mu is 0.15, and my normal reaction is 4g cos 30. So I'm going to leave it in terms of g and cos 30 at the moment. That is our value of friction. I could get an exact value for that. Cos 30 is √3/2, which obviously you all knew because you've learned your exact trig values like we're always telling you to. But at the moment, that's more use to me for what I'm now going to do with it. So I've resolved perpendicular to the plane. I'm now going to resolve parallel to the plane. And again, in the same way as when I looked perpendicular to the plane, I stood my ruler on here and looked at all the forces acting in this plane. I'm now going to look at all the forces acting parallel that are acting on A. So as I slide down here, you can see you've got T, which is acting up, F, which is acting down, and sliding down, look, 4g sine 30. That's the weight component down the slope. That's the one that everybody always forgets. So, how we're going to do this is we're going to use our resultant force equals mass times acceleration. The force acting up the plane was T, minus F for friction, minus 4g sine 30. And that is going to equal mass times acceleration. Now, because we're only looking at particle A, the mass is 4. So it's 4A. And I can now get all this to be T minus a single value. And this will be my first equation of motion that will help me ultimately to find out T and A as numbers. So, T minus friction, we know, is that. It's 0.6 g cos 30.